The separation of mixtures of propylene and propane is of industrial importance because of the need for producing feedstocks to the polymerization reactor. The purity requirements for polymer grade feedstocks is that the propylene content be purer than 99.95%, and currently such purities are achievable in distillation separations due to the small differences in the boiling points of propylene and propane. Cryogenic distillations are necessary, and such distillation columns are operated at high pressures and high reflux ratios because the relative volatility is close to unity. It's 1.14. We ask ourselves the question whether metal organic frameworks can provide energy efficient alternatives to propylene-propylene separations in PSA units. Many MOFs selectively adsorb the unsaturated propylene by exploiting the pi bond interactions with open metal sites of m-MOF74, where M is magnesium, iron, cobalt, nickel, or manganese. Alternatively, we may selectively adsorb the unsaturated alkene by interactions with extra framework cations of zeolites such as 13X or LTA5A. A completely different strategy for separating propylene-propane mixtures is to exploit the subtle differences in the bond lengths, bond angles, and molecular shapes and sizes of propylene and propane by using ultra microporous cobalt gallate as described in this paper in JACS 2020. Another alternative is to use KAUST-7 that has a subtle trapdoor mechanism that excludes the saturated propane from the pores of KAUST-7. We examine separations with these two different strategies and examine which of these two strategies is capable of yielding polymer grade feedstocks suitable for polymerization reactors. In this graph, we compare the breakthroughs for 50-50 mixtures of propylene and propane in the adsorption phase of a fixed bed adsorber. The graph plots the dimensionless concentrations at the exit as a function of a modified time parameter, where T is the time in seconds, Q0 is the volumetric flow rate of the gas mixture at the inlet in units of liters per second, and this quantity is divided by the mass of the adsorbent in the bed. We note that there are important differences between the breakthrough characteristics of iron MOF74, denoted here in red, and the other two MOFs, KAUST-7 and cobalt gallate, that rely on exclusion of the saturated alkane from the pores by exploiting subtle differences in molecular shapes and sizes. For iron MOF74, the uptake capacities are significantly higher than those obtained with these two MOFs, However, we note also that there is a significant uptake of propane along with that of propylene. So this significant uptake of propane within the pores has important consequences on the purities of the propylene product in the desorption cycle, as we shall see in the subsequent slides. In contrast, these two MOFs virtually exclude propane from the pores, and the breakthrough of propane occurs practically at the start of the adsorption, nearly start of the adsorption run. But the amount of propylene that is adsorbed is significantly lower by about a factor of 5 than the uptake capacity of MOF 74. So let us examine the important differences between the productivity and the purities obtained with these two different classes of adsorbents. I now compare the adsorption and desorption cycles for two different MOFs, cobalt MOF 74 and KAUST-7. These two MOFs have two different strategies for propane-propylene separations. Let's look at the simulations of the adsorption cycle. The breakthroughs with cobalt MOF 74 are indicated by these black lines, and the breakthroughs with KAUST-7 are indicated by the blue lines. For cobalt MOF 74, there's significant uptake of both propylene and propane, whereas with KAUST-7, propane is practically excluded from the pores. However, the uptakes of both components are significantly lower than the uptakes with cobalt MOF 74. At the times indicated here, we have the termination of the adsorption phase, and the desorption cycle is simplified in the following manner. It consists of a counter-current vacuum blowdown. Deep vacuum is applied, and the pressure at the exit is assumed to be 2 kilopascals. The simulations of the counter-current vacuum blowdown operations are shown here. Black lines refer to cobalt MOF 74, and the blue lines correspond to KAUST-7. Let's look at the cumulative moles leaving the vacuum blowdown operations with the two MOFs. We note that with cobalt MOF 74, a significantly higher amount of propylene is recovered, about 5 to 6 moles per kilogram of adsorbent, but concomitantly we have a significantly high amount of propane also being recovered in the blowdown phase because of the significant amounts of propane that remains in the adsorbed phase at the start of the blowdown operations. In sharp contrast, with KAUST-7, the amount of propylene that is recovered is significantly lower, but so is the amount of propane that is recovered, and the propane that is recovered is about an order of magnitude lower than the propane that is recovered with cobalt MOF 74. These differences in the amounts of propane that ends up in the product here is reflected in the purities. with KAUST-7, a purity of 98.7 is achievable in the simple PSA scheme of adsorption and desorption, whereas with cobalt MOF 74, the maximum purity that is achievable is only 92.5. So with a simplified PSA scheme, neither of these two MOFs is capable of producing polymer grade propylene, but with cobalt MOF 74, the maximum achievable purity is significantly lower than the purity achievable with KAUST-7. The message to emerge is that to achieve high purity, the uptake of propane in the adsorption cycle should be close to zero. We need to have total exclusion, otherwise the purity requirements are difficult, nay impossible to achieve. One remedy is to have a more complex PSA scheme, as we shall see in the subsequent slide. In order to increase the purity of the recovered propylene, we need to employ a 5-step separation, PSA separation scheme shown in this slide. This scheme consists of pressurization, adsorption at high pressure, followed by co-current high pressure purge, and the purge is with the product propylene. This is followed by co-current blowdown operations, followed by countercurrent vacuum blowdown. Any propane that remains in the void volume will contribute to loss of purity of the desired propylene product. And in order to mitigate that, we introduce the co-current high pressure purge in the step here.